Hi. In this video, we'll be giving 3 examples of vector spaces. This will allow us to apply the definition of a vector space that we learned last time. The first example we'll start with is called f infinity. We would like the underlying set of this space to be the set of all sequences with entries in f. Formally, we can define this set as follows. So f infinity is defined to be the set of all sequences x0, x1, and so on, where each entry xj in the sequence is an element of f, and the index j is a natural number. Another way to view this set is as the set of all functions from the natural numbers to our field f. And by convention, we denote the set of all functions from n to f by f superscript n. So if you've never seen this notation before, it might be a bit confusing at first. So f superscript n is actually the set of all functions that is going from n to f, and not the other way around. To show that this equality marked in purple is true, we need to show both inclusions. So to start off with, if I'm given some sequence x0, x1, and so on, where each of the entries xj is an element of the field f, then I want to get a function from the natural numbers to f. And so how do I do this? Well, I can just set f of n to be the entry x sub n. Or in other words, I'm assigning the natural number n to the entry x sub n. And now, since for every natural number n, there exists some entry xj, which is an element of f, this rule down here indeed defines a function from the natural numbers n to our field f. So the below argument shows that we have this inclusion. That means that the set of all sequences is included in the set of all functions from n to f. Now, to prove the other direction, suppose we're given some function f which goes from the natural numbers n to our field f. This means that each natural number, small n, is assigned a value f of n, which is an element of the field f. We can now get a sequence determined by this function as follows. We just set our sequence to be the sequence f of 0, f of 1, f of 2, and so on. And since our function goes from the natural numbers to our field f, each of the entries here is an element of our field. So indeed, this sequence that we've constructed lives up in this set here. So we've just shown that for each function from n to f, we can get a corresponding sequence with entries in f. So this proves the other inclusion. And so this shows that indeed what I wrote before is correct. We have an equality between these two sets. Okay, so far we've defined this underlying set of f infinity, and I've given you 2 ways to look at it, either as the set of sequences with entries in f, or as the set of functions from the natural numbers to our field f. And to make this a vector space, we need to introduce addition and scalar multiplication operations on this set. The way we're going to define addition on f infinity is going to be familiar to us because we've already seen the same idea for fn. We just do component-wise addition. So what this means in concrete terms is that given the sequence x0, x1, and so on, and the sequence y0, y1, and so on, we define their sum to be a new sequence which has entries x0 plus y0, x1 plus y1, and so on. And now we note that this definition makes sense because each of the elements x0 and y0 is an element of the field f, so we can form their sum in f, and get another element of the field f. Finally, we need to define a scalar multiplication. This should again be familiar. Given some lambda in f, we define the scalar multiple of a sequence x0, x1, and so on, simply to be the sequence that contains as entries lambda x0, lambda x1, and so on. So this is again the same definition that we saw in the case of fn, and we note that since lambda is an element of f and x0 is an element of f, their multiple lambda x0 is again an element of f, so this definition makes sense. We can now state the expected proposition, namely that f infinity is a vector space over the field f. For the proof of this proposition, we need to make an observation, and that is that for each component of a sequence in f infinity, the addition and the scalar multiplication are defined precisely in the same way as they were in fn. And now if we recall how we proved the properties for fn to be a vector space, what we did was we chose an arbitrary component and then showed that that property held for that component, and then generalized the statement that this property holds for all the components and thus for the element in fn. Now, since addition and scalar multiplication in f infinity are defined on a component by component basis, and this definition is exactly the same as it is in fn, we can apply precisely the same proofs we used to prove that fn is a vector space for f infinity. So essentially I can just paste the same proof that we used for proving that fn is a vector space here. However, we need to make sure to replace each element of fn in that proof with a corresponding element in f infinity. So if this seems mysterious to you, I encourage you to try to prove this proposition for yourself, and you will quickly realize that you can apply exactly the same proof as we had previously for fn to the space f infinity. Regardless whether you go through the entire proof for yourself, you should at least think about what the zero element in f infinity should be and what the additive inverse for a given element should be. The second example we'll look at, fs, generalizes both fn and f infinity. We want the underlying set of the space to be the set of all functions from a fixed set S to our field f. We can write this compactly as follows. Fs is the set of all functions f from S to f. We can visualize an arbitrary element f of fs as follows. So we draw the set S and we draw the set f. And now S will contain some elements and f will contain some elements. And the function f now maps the elements of S to the elements of f. In order for fs to be a vector space, we need to somehow define an addition and a scalar multiplication on the elements of fs, which are, in this case, functions. If we have a second function, g, which also lives in fs, then g maps, again, the elements of s to some elements of f. Our job is now to find a way to add these objects f and g. And in order to do this, we'll exploit the fact that the set that they're mapping into, f, is a field, and in f we can add objects. Thus we want to construct an element f plus g, which also lives in fs, so is a function from s to f, and we do this as follows. So because it's a function, we need to assign each element of s an element of f. And so we'll just focus on this one element marked in red. we see that f maps this red element to this blue element, which I'll call x, and that g maps the same red element to this green element, which I'll call y. We now need to decide where f plus g should map the red element. But since f is a field, there exists an element x plus y in f, and we define f plus g in the following way. We just map this red element to x plus y. If we call this red element here on the left a, we can write what we just did out in a formula. So we defined f plus g, so this is the sum function of a, to be x plus y, and x is just the image of a under f, so x is f of a, and y is the image of a under g, so this is g of a. So in effect, what we did was we defined f plus g of a to be f of a plus g of a. And now we can simply repeat the same procedure for each element of S, and this will define a function f plus g on the entire set S. The case of scalar multiplication is even simpler. So given some function f in fs, we want to generate a function lambda f in fs for some scalar lambda which lives in f. And how do we do this? Well, we do a similar thing as we did for the addition. If we want to define a new function, we again have to decide where to map an element of S. So in this case, we focus on the red element again, which I'll call A. And so f maps this element A to x. And now, because f is a field, there is some element in f, lambda x. So this is the multiple of x by lambda. And this exists because f is a field. And now we can define the function lambda f to be the function that maps the element a to lambda x. So in formulas, this becomes lambda f, our new function, of the element a is defined to be lambda times x, but x is just the image of a under f. So this is lambda times f of a. And as before, this works for each element of S, so we can just repeat this procedure for each element and get a function from the entire set S to f. Let's summarize the results of our discussion. So let f and g be elements of fs, and lambda be an element of our field f. Then we make the following definitions. We define the function f plus g of an element x of S to be simply the sum of f of x and g of x. And we do this for all elements x in S. And similarly, we define the function lambda f of an element x to be lambda times f of x. And this is again for all elements x in S. I'd like to stress that this side of the definition only makes sense because f is a field. If f were some arbitrary abstract set, we wouldn't have an addition and a multiplication in f, so we wouldn't be able to make these definitions. So in general, we're not able to add or scalar multiply functions, but because f has this additional structure, we can exploit this in order to define new functions based on these operations. And this is in fact a general phenomenon. So if we have functions that map into a set that has some additional structure, we can transfer that additional structures to the functions themselves using analogous methods that we used here for defining the sum and the scalar multiple of functions. To make this all a little more concrete, we can consider the following example. We set S to be the interval 0, 1, and we set f to be the real line. So in this case, fs is equal to r superscript 0, 1, and this is just the set of all functions going from the closed interval 0, 1 to the real line. Two elements of this set might be the function g, defined by g of x equals 3x, and say a function h, which is defined by h of x is equal to e to the x. In this case, their sum, g plus h of x, would be defined by the formula 3x plus e to the x. Well, if we want to calculate the function 3 times g of x is just 3 times 3x, which is 9x. Finally, we can make the following observations. We saw before that we can think of the underlying set of f infinity as the set of all functions from the natural numbers to f. And so now we see that this is just a special case of fs, where we set s to be the natural numbers n. In fact, the addition and scalar multiplication defined above reduce to those that we defined for f infinity in this special case. To show this, we can take two sequences, x0, x1, and so on, and y0, y1, and so on. And we saw that we can think of these as functions where each index is mapped to the corresponding entry. So the natural number 0 would be mapped to x0, the natural number 1 would be mapped to x1, and in the case of the second sequence, the natural number 0 would be mapped to y0, and the natural number 1 would be mapped to y1. So we could now call the functions here that are induced by the sequence, we could call this, for example, fx, and the other one fy. If we want to determine what the function fx plus fy is in the space fs, then fx plus fy of a given element, say 0, is defined to be fx of that element plus fy of that element. And if we check over on the right, fx of 0 is just x0, and fy of 0 is just y0. We can now observe that this on the left-hand side is just describing the 0th coordinate of the sequence x0, x1, and so on, plus y0, y1, and so on. So this is the 0th coordinate of the new sequence we obtain by adding the sequences. And this equation down here is saying that the 0th coordinate of this sum sequence is just x0 plus y0, which is exactly the definition we made in the case of f infinity. Similarly, if we let S be the set containing the numbers from 1 to n, then fs is actually the same thing as our vector space fn. We can see this as follows. So fs contains functions f from s to f. So f will map the element 1 to an element of f x1, and the element 2 to an element x2, and so on, up to n, which gets mapped to some element xn. But now we see that what's down here is just a vector that lives in fn. So starting with a function in fs, we can get a vector in fn, and conversely, starting with a vector in fn, this defines a function that assigns each natural number n the entry xn. Finally, the operations defined on fs also reduce to those in fn. And to see this, we simply note that vectors in fn are basically infinite sequences, so elements of f infinity that are just truncated at some point n. So the same argument I used before to show that addition in f infinity is a special case of addition in fs also shows that addition in fn is a special case of addition in fs. After all this effort, we would surely hope that the following is true. fs is a vector space over f. So I'm not going to prove this entire proposition, but instead just give an outline of what we need to show. and then I'll give an example of one of the parts of the proof. In order for something to be a vector space, we need three things. First, we need the structure V plus times, so we need a set V, an addition on that set, and a scalar multiplication on that set. Now usually if we're trying to prove that something is a vector space, we already have this structure as a given. Second, the definition of a vector space requires the existence of an additive neutral element and additive inverses. Usually if we're trying to prove that something is a vector space, we need to determine what the zero and the additive inverses are, and this will then be part of the proof. And third, the above need to satisfy the equations that we have in the definition of a vector space. We can group this as follows. A and B could be called the data of a vector space, and C could be called the properties that these data are required to satisfy. In our case, A is already given, so we have the definition of the set Fs and the operations on that set above. And in what follows, I will show B, so the existence of the zero and the additive inverses, and I'll show one of the identities in C. Let's start by determining the zero element. So the zero element needs to satisfy f plus 0 is equal to f for all functions f in Fs. We notice that this equality here is an equality of functions, and two functions are deemed to be equal if they act the same way on all elements in their domain. So the above implies that f of x plus 0 of x needs to be equal to f of x for all x in S and for all f in Fs. We need to watch out here. This 0 of x might look a bit weird, but the 0 is not the number 0, but is actually the 0 element in Fs, and so it's a function, and so we can evaluate it at the point x. Okay, so we want our 0 element in Fs to satisfy this condition on the bottom, and we note that each of these elements is an element of our field F, since elements of Fs map objects in S to objects in our field. Now we already know of an element in F that has this property that we're requiring, namely that if we add it to some other element of F, we get back the original element, and that's just the element 0 in F. In fact, this 0 in F is uniquely determined, which means that we're forced to choose the 0 in order for this equation to hold. Moreover, since this equation needs to be satisfied for all elements x of S, this means that 0 of x has to equal 0, so this is the 0 in the field F, for all x in S. And this uniquely defines the function 0 from S to F. So all of this shows that the 0 element in Fs is the function from S to F that maps each element x of S to 0. Next, we want to see what the additive inverses should be. For this, we let f be an element of Fs, and then its additive inverse needs to satisfy f plus minus f should be 0. Now, from the preceding discussion, we already know what the 0 element in Fs is, namely the function that maps every element of S to 0. So in terms of individual elements, this above equation for the function equality becomes that f of x plus minus f of x should be equal to 0 of x, but that's just 0, and this should hold for all x in S. We may repeat the previous strategy by noting that each of these elements is an element of f, and now this equation is saying that if we add an element of f to another element of f, we get 0. And we already know of such an element, namely the additive inverse of that corresponding element in F. Because additive inverses in F are unique, we are now forced to set minus f of the element of x to be minus f of x, where this minus on the right-hand side signifies the additive inverse in F. Moreover, we require this equality to hold for all elements x in S, so this definition down here defines a function from S to F, which is the additive inverse in Fs of F. Therefore, the below shows that the function minus f from S to F has to be defined by assigning each element x to minus f of x. So we've now shown B, and I will show one of the identities required in C, namely commutativity. So what we need to show is that f plus g is equal to g plus f for all f and g in Fs. Here we are again confronted with an equality of functions, and we remember that two functions are considered equal if they have the same domain and if they map each element of the domain to the same element in their codomain. So in our case, this translates to the condition that f plus g of x needs to be equal to g plus f of x for all x in S. But by definition, for any element x, f plus g of x is equal to f of x plus g of x. But now this addition here is happening in the field F, where addition is commutative, so this is equal to g of x plus f of x. Now applying the definition of the sum of two functions in Fs in reverse, we get that this is equal to g plus f of x. Since x was arbitrary, this holds for all x in S, which proves the required equality. The proof of the other identities is very similar, so it doesn't really contain any new ideas. We just need to be careful that we're always aware of where the respective additions and multiplications are taking place. So if it's in the space Fs or if it's in the field F. And the strategy is generally just to reduce some property in Fs down to the corresponding property in the field F. So I'll skip the proof of the rest of these identities and move on to our final example. One could argue that so far we've actually just seen one example of a vector space, namely Fs, because the other examples that I've presented are just special cases of Fs. To see an example of a different type of vector space, I'll briefly touch on polynomials. The following will just be an outlook, so I'll go through this very fast. However, in 3 videos, we'll see a more detailed explanation of polynomials and how the operations on polynomials work. So we define a polynomial P with coefficients in F to be a formal expression of the form P of z is equal to a0 plus a1z plus so on up to an to the zn. And here, the coefficients a0 up to an are elements of F. Now let am be the coefficient of largest index that satisfies am is not equal to 0. Then we say that the polynomial P has degree m. So for example, if an were non-zero here, this polynomial P would have degree n. We can now define two sets, namely P of f which will be the set of all polynomials with coefficients in f. We can also define a second set, P sub m of f, which is the set of polynomials with coefficients in f of degree at most m. We will see in a future video that both of these sets are actually vector spaces over the field f. And if you've seen polynomials before, I encourage you to think about how we would define addition, scalar multiplication on these sets, and what the zero element and the additive inverses should be. This brings me to the summary of this video. So we saw 3 examples of vector spaces, the first of which was f infinity, the set of all sequences with entries in f. Then we saw the vector space fs, which is the set of all functions from s to f. And finally, we got a glimpse of the vector space P of f, which is the set of all polynomials with coefficients in f. Moreover, we saw that f infinity and fn are special cases of the space fs. So this begs the question of how P of f is related to f of s, which is something you can think about. Okay, next time we will move back to a more general setting and prove some basic properties of vector spaces. And I hope to see you then.